Hi, my name is Balázs Holzer from Budapest, Hungary, and welcome to my course on face recognition in Java. First of all, let me tell a few words about myself. I'm from Budapest, Hungary, as I said earlier. I'm qualified as a physicist, and later on I decided to get a master's degree in applied mathematics. Currently, I'm working as a software engineer at a multinational company, and I have a special addiction to models concerning quantitative finance, such as the Black-Scholes model, modeling credit risk, and how to use machine learning and artificial intelligence techniques in order to make some forecasts. So what you are going to get from this course? We are going to talk about how to use OpenCV and of course face detection with the help of Java. And we are going to have the complete project and the complete Java implementation as well. It's very important that there is an HD option for every video, so if you find the video blurry, you just have to set it to HD as you would do it on YouTube, for example. So thanks for joining my course. Let's get started. Hi, in this video we are going to talk about the theoretical background of face detection, so let's get started. First of all, we are going to use the OpenCV library, and it is the most popular face detection library. It can be used for Python, it can be used for C++ or Java, so it is very convenient. As far as I know, it stands for Open Source Computer Vision, and it was started by Intel in 1999. Of course, it was written in C and C++ because the algorithms are very computational heavy behind face detection, and these kinds of problems can be easily solved with the help of C and C++, and not just easily but efficiently. And the main problem is that face recognition is very easy for human. Even, for example, a children at the age of 1 or 2, it's very easy to detect cars, for example, or birds, or trees, or faces in the main, but it's very hard for computers. And why? Because computers, instead of the images, computers are going to transform the image into a matrix of numbers. So we have an image, and it is going to be converted to numerical data. And we have to make some algorithms on these numerical data in order to be able to make good predictions. And this is why it's very hard for computers. So there are lots of approaches. For example, the first approach is the geometric face recognition. It is probably the most intuitive approach to face recognition. Marker points should be constructed, and these marker points are position of eyes, ears, and nose. So we create features on these parameters, on these marker points, the distance between the points or the angle between them, so these will be the features. And the recognition is performed by calculating the Euclidean distance between feature vectors of a probe and the reference image. I'm not sure whether we are familiar with KNN machine learning algorithm, but it's approximately the same. We calculate the Euclidean distance and we are going to classify accordingly. Of course, it has some advantages as some disadvantages. The advantage that it is robust against changes in illumination. But the disadvantage is that it's hard to construct the feature vector. So it is not a very good approach. The next method is the so-called eigenfaces method. A facial image is a point from a high-dimensional image space, and a lower-dimensional representation is found where classification becomes easy. And of course, a lower-dimensional subspace is found with the help of principal component analysis, with the help of eigenvectors and eigenvalues, and that's why the name came from eigenfaces. So it's kind of a math-heavy process, and linear discriminant analysis is applied to face recognition too in this phase. But it's not a very good method. Machine learning approaches becoming more and more popular because in the late 1990s, for example, using neural networks was not so easy. It took a lot of time to train our algorithm, but with the help of the modern computers, these calculations can be performed very, very fast, and that's why machine learning algorithms again are very, very popular. So what's the fundamental basis of machine learning algorithms? Of course, we have a huge training set, lots of images of faces, different lighting, different facial expressions, and so on. And why is it good? Because we have this training set and we can train our model on this so-called training data set. We can use, for example, support vector machines, SVMs, or neural networks. Both of them are very good. And then after training the model, we will be able to detect faces after the learning. By the way, for example, support vector machines and neural networks are able not just to detect, but to recognize the face. And that's how, for example, CCTVs work, that it is able to detect a given person, not just the fact that, okay, we see that there's a face, but it can make a good prediction on who this face belongs to. So this machine learning approach is very good, but the OpenCV relies on Cascade method, which starts at the top left of a picture and moves down across small blocks of data, looking at each block. OpenCV Cascade breaks the problem of detecting faces into multiple stages. For each block, it does a very rough and quick task, and this is why it's important, because this Cascade method is very fast. Machine learning algorithms, for example, training a neural net, can take a lot of time. This Cascade method is very fast on the other hand. So if this block passes the test, it does a slightly more detailed test and so on, in order to be able to have a guess whether that's a face or not. The advantage is that the majority of the pictures will return negative during the first few stages, and the algorithm will not waste time testing all features on it. So it does a rough quick test, and it makes a good prediction whether, okay, it may be a face, so it's going to make some calculations again. But if it comes to the conclusion that, okay, it is not a face, it goes on. So it works something like this. We have an image. I just draw some random lines. We start at the left upper corner, and we shift our window to the right, and again to the right. And each of the iterations, we pose the question, is it a face? We come to the conclusion that, oh no. And of course, in this picture, there is no faces at all. So the last few steps will look like this. The last few steps, we pose the question, is it a face? Is it a face? And no. So we keep building small blocks, this small white window, and we keep shifting it from left to right, from the upper corner to the lower corner, and pose the question, is it a face or not? And if we come to the conclusion that it may be a face, our algorithm is going to do some further calculations. So this Cascade techniques is very, very good. So that's all about the theoretical background. Thanks for watching. Hi, in this video we are going to talk about how to install OpenCV for Windows. If you are on Linux, I think it is very, very easy. With the help of command line, you just have to print the apt get sudo install and so on. For Windows it is a bit more trickier. You have to download the OpenCV for Windows, you have to install it, and it's very important that, as far as I am concerned, it is not necessary to set the environment path. Only if you use it, for example, for Python and so on, because this OpenCV library is written in C and C++, so you can use it with the help of Python, for Java, for C# and so on. So I think, because configurations are the most complex problems in software engineering as far as I am concerned, it is advisable to do so. It is in Hungarian, so you are not likely to understand it, but this is the special system settings. This is the so-called environment variables. And first of all, we are going to, this is the edit and the delete function and so on. So first of all, we are going to create the OpenCV accordingly. So I'm going to look for the, okay, OpenCV there. And you have to create a news. You have to click on the new one. Where the name of the variable will be the OpenCV. I'm not going to do it because I have already done it. And the value of the variable will be the place you have installed it. So I have installed it on the C, OpenCV. It's very important that under the build x64, because I have a 64-bit machine, I mean processor, and we C12, we have to reference it. And after we have done it, we have a variable with the name OpenCV there, and we have reference where we have installed it. We have to add it to the path. So you have to edit your path, and you have to copy this. The person sign, of course, you like this. So a semicolon, a percent, then the OpenCV there. With the help of this, we are going to reference this variable. And then we have to reference the bin. We have installed it, and in the bin file, there are the files that are very important for Java to run it. By the way, with the help of the installation, we get several jar files, and that's what we are going to import in our project in order to use OpenCV for Java. So that's all about the configuration part. Thanks for watching. Hi, in this video we are going to talk about the general user interface part of our application. And because this is not a video about GUI in Java, we are not going to develop it from scratch. We are going to talk about it in this video. And of course you can download the source code and copy and paste the content, whatever you prefer. Okay, so our application consists of a face detector. This is the title of the application, and is a very simple one. We are able to exit our application, we are able to load images, and with the help of this navigation tab we are able to select and choose an image on which we would like to run our face detection algorithm. And when we detect faces, we click on this, it is going to show the detected faces for us. So our loaded image will be centered in our application, and that's the reason for this application. So it's very simple. First of all, this try and catch blocks is very important to load the system look and feel. And it means that if you are on Windows, like I am, it is going to show the system, the Windows 8 features. As you can see, my application has the border. It is a typical window-like application with the color, the fonts, the text, and so on. So everything is Windows look. If we would run this application on a Mac, for example, because of this line UI Manager set look and feel, our application would look like a typical Mac application. If we run our application on a Linux Ubuntu, it is going to get the system look and feel, and because that system is not Windows, it is Linux, it is going to get the Linux look and feel. So this is, I like to make it in my code. It's not so important. With the help of the Swing utilities that invoke later, we are able to create a single distinct thread for our application. It's like writing new thread, new runnable, and so on. And we just have to start our thread. Here it's very easy. With the help of Swing utilities, we are able to create a distinct thread for our mainframe. And our mainframe is going to contain everything within our application. This time we only have the image panel, and this image panel is going to contain the image on which we would try to run our face detection algorithm. We are going to develop the image loading feature in the next video. Then in the coming videos we are going to talk about the face detection process itself. So the mainframe is going to store a reference to the image panel. it has the J-file chooser. Why is it important? Because if I would like to choose a file, choose an image, if I click on the load image, this is the J-file chooser. So that's why I need it. Of course, I will have the face detection. This face detection is an empty class. It is going to contain the face detection algorithm itself. And of course, I have to specify the application name. I like to create a constant class with a private constructor. Why is it good? Because if a class has a private constructor, you will be not able to instantiate it. It is going to store references to static final variables such as strings, the name of the application. Do you want to exit? It is going to show up when you try to exit, the frame width and the frame height, the image label border, and so on. Why is it good? Because if you want to make this application, for example, Spanish, then you just have to go to the constants and you have to change every string to Spanish, from English to Spanish, and that's how you internationalize your application. So I like this. I like this approach. Okay, so we set the J menu bar. What is the menu bar? The menu bar is the one. I'm not going to close it anymore. Sorry. The menu bar is this. You are here, the file, the about, and the help, and that's what we like to construct. And this is the ZJ menu bar. In the J menu bar, we are going to create a menu, the file menu. Then we are going to J menu items, load image, detect faces. So these are the menus, and these are the menu items. One a menu item, two menu items, three menu item. And we can set action listeners to them in order to be able to detect whether we have clicked on this menu item or not. Okay, I have created several others, the about and the help and so on. If I click on the exit menu, I'm just going to, it means that J option yes no option, it means that if I click on the yes, so it's going to pose the question, exit. Do you want to exit? If I click to no, it's not going to exit. If I click to yes, we just system garbage collect and system.exit with 0. Okay, so this is about the create menu bar. I'm just going to instantiate or classes the J-file chooser, the face detection, which contains the algorithm, image panel. We add it to the border layout center. It means that we are going to add it to the center of our application because that's what we are after. And of course, set the size. The frame width and the frame height is just the dimensions of our application. If we set it the width, for example, twice as the value now, it is going to be twice as wide, and so on. So nothing special. Set visible true to be able to visualize it. The close operation exit on close means that if we click on this, it is going to dispose our application. Set location relative to this, it is just to, if I run my application, where will be the starting location? It doesn't matter, by the way. If I get rid of this, it's going to be the same. Okay, so with the help of this set relative location, we can specify that when we start our application, where will be the location, here, here, or just here at the left upper corner. I think it's not so important in our face detection concept. Okay, so we have the image panel as we have discussed. We are going to store our image on a J label. And in the constructor, we just instantiate the J label. We set the layout to border layout, and we set the border with the border factory create empty border image with the image label border. It means that if we wouldn't use borders, it wouldn't be so fancy. If we use a with border, it is going to center our image with a little padding and margin on the outside. So that's why it's a bit nicer. And of course, we add the image label center. So this is our application. We can load the images, but it's not going to be shown up here. And that's what we are going to code together in the next video. So that's all about the basic general user interface construction. Thanks for watching. Hi, in this video we are going to talk about how to load the image to the image panel. So I have created three methods. First of all, the update image method. It is just going to set the icon on the image label, and as we have discussed, this image label is just a simple J label. So we are going to attach an image to this J label and it's working fine. So we're just going to set the icon. We have to use the image icon, so that's why I instantiate a new image icon here. And we have to scale the image because there may be different sizes of images, such as one image has a very, very small width, the other image has a very, very large height, and so on. So we have to scale it. And how can we scale it? Just image.getScaled instance, we have a method like this. We have to specify the width, we have to specify the height, and we have to specify the method, and I'm going to use the smooth scaling method. It is just going to do everything for us in the background. And we have the load image. We have to specify a file such as //user desktop profile.png JPEG or so on. So we have to specify a file. And I'm going to store a reference to the transferred image icon, and I'm going to instantiate it according to the absolute path of the file. Then I'm going to create an image with the help of the transformed image icon.getImage, and I'm just going to update the image with this concrete image. And of course it's going to call the scale image, and it's going to set to the J label, to the current according to the file which we have read. So here in the main frame we have to specify this. We have selected the file. I'm going to system out the mainframe.this.file. So if I'm going to run my application and I'm going to load the image, for example, I will use the desktop, Udemy, machine learning, face detection, and I will have some images, for example this. I have printed out the system out println. So as you can see, this is the file c:/users user desktop Udemy image.jpeg. And then I'm going to load the image, and as you can see, I have successfully loaded the image. If I would like to load another image, for example the image 2, it is going to be loaded without any problem. A better solution to use loading panels, which means that as you can see, loading is a bit slow, and the user thread, I mean the main thread, the application thread, is going to be blocked for the loading process. So we should use progress dialog and so on, but I'm not going to bother about it. So these are the images. And I would like to use my face detection, and that's what we are going to implement in the next video, to be able to detect the current faces on the given image. So that's all about this video. Thanks for watching. Hi, in this video we are going to implement the face detection algorithm with the help of OpenCV together. So first of all, you should import the OpenCV.jar, and you can do it. In the previous videos we have discussed how to install the OpenCV library, and after you have installed it, you can go to the properties, Java build path, add external jars. You have to go to the OpenCV where you have installed OpenCV.build Java, and you have to open this OpenCV. It is the 3.00. Approximately the latest version of OpenCV, and of course you have to open it. I'm not going to open it because I have already included in my project. Okay, And it's very good because we can now use the library, the methods and classes of OpenCV, and that's what we are after. So first of all, I'm going to create a Cascade classifier. If you may recall, the Cascade classifier is what we are going to use. It is the most efficient way of detecting faces. Cascade classifier. Then in the constructor, I'm going to public face detection. We have to load the system load library, the core.native library name. We have to load the native library. Okay, then I'm going to instantiate this Cascade classifier and Cascade classifier, and we have to specify constants.cascade classifier, and in the constants file we have our constants. The Cascade classifier is going to store a reference to the hair cascade frontal face.xml. That's what describes that according to what this algorithm is going to detect the faces. I'm going to upload it with the source code. You can download it, and you have to reference the location of this XML file. As I said earlier, but I don't want to repeat myself over and over again, it's very important, this file, because this contains the information that our algorithm knows that what are the most important features in a face to be able to detect. So for example, if two eyes are there in a picture close to each other, a mouth and a nose in the middle, then it is probably a face. So that's what this hair cascade frontal face alt.xml is going to define for us. Okay, so we have to reference it, and we have to use it when we instantiate the Cascade classifier. Then I'm going to have a method public void detect faces. I'm going to have a file, the image which we have loaded with the help of the user interface, and the reference to the image panel to be able to update our image panel accordingly. Okay, so first of all we have to create a mat. This is a matrix containing information about the image. So this is the image is equal to img codex dot image read, and we have to specify the file that get absolute path, not absolute file, absolute path, img codex dot cv load image, and I'm not going to use grayscale. I'm going to use image color. Okay, this math is a library org.opencv.core. So these classes are all included in the OpenCV jar. This what we have included. Okay. Then I'm going to have a matrix of rectangles. Rect. These will be the face detections or detected faces. New math of rects. Math of rects. Okay. Then in the Cascade classifier, we have to use the detect multiscale, and first of all I'm not going to bother about the constants. In the next video we are going to talk about how to tune a Cascade classifier. We can specify that what are the parameters of the faces. If a face, for example, in the background, it is going to appear smaller than it would be in the foreground of the image. So we can specify these kinds of parameters, but these have a standard value. So we try our algorithm in the standard way. So we have the image and we have the face detections. The detected faces will be copied to these face detections. and I just have to iterate through rect. This rect stands for rectangles, face detections dot to array, and okay, I have to import the OpenCV.rect, and I have to print. I have the image, and I would like to show the rectangles on the faces, so I have to paint rectangles for every detected face. We have the detected faces, we iterate through them, and we paint a red rectangle on the faces to be able to show it. So imgproc that draw a rectangle. I'm going to import it. imgproc. Okay. So first of all, I have to specify the image. Then I have to specify a new starting point. It is going to be the rect.x, the rect.y. Then I have to specify the endpoint of a rectangle. It's going to be the rect.x plus rect.width plus rect.y plus rect.height. Then we have to specify the color codes, new scalar for the red, green, and blue channels to be able to specify the color with which we have to assign for these rectangles. Okay, for example, 100, 100, 250. You can play around with these numbers, whatever. And the line width is going to be set to 10. Okay, and I'm going to import this point, OpenCV.core, and the scalar org OpenCV.core. Okay. And of course I have to use okay something like this. So the last step is to tell the image panel to update the image with the detected faces. So first of all, I'm going to create a buffered image. Buff image is going to be convert mate to image. We have to convert, and it's going to our private method because we have a matrix as an image, and we have to convert it to a buffered image to be able to use it with Java. Image panel dot update image on the buffered image. Okay, so here first of all I have the image. Okay, I have to decide whether it's going to be a grayscale or it's going to be a colored image. So the type is equal to the buffered image dot type byte gray. So if the mat.channels, image, if the image, I'm going to call it mat because it's just a matrix that represents the image, of course. The channels is the red, green, blue, for example, the components and so on. So if it's greater than 1, then the type is equal to BGR, blue, green, red image. So buffered image dot type 3 byte BGR. So the default that we assume that it is going to be a grayscale, and if it's not, we set it to a colored image. We have to calculate the buffer size, and it is equals to the channels, because for every channel we have to calculate the columns and the rows. So mat.color calls times the math dot rows, because we can have multiple channels, one channel for the blue, one channel for the green, one channel for the red, and it is going to be multiplied with the columns by rows. Okay, I'm going to create a byte array for bytes with the buffer size. I'm going to get all the pixels from the image, 0 from the 0 row, from the 0 column, and of course for the bytes. Okay. Then I will have a buffered image. It's going to be the image that we have converted, the new buffered image. And I will have the math.columns. I have to specify the math.rows, that how many rows and how many columns do we need. And then here I will have the type. Okay, because this is a type, whether it is a grayscale or a colored one. So it's going to be the image. I will have a final byte, the target pixels. Data, I'm going to cast it to a data buffer byte. Image dot get raster dot get data buffer. Okay, and I have to get the data. So these will be the target pixels, and I'm going to use system.arrayCopy bytes from 0, of course. Then for the target pixels, I would like to copy for the target pixels from 0. And I have the bytes.length. I have to specify the length of the bytes I want to copy. And then that's all. I'm going to return the image. So why is it important? Because we calculate with matrices, and the matrices are full of numeric data, numeric numbers. And we try to transform this matrix into an image to be able to set it to the image panel, and we try to show the detected faces. So that's all about these parameters. It's very important. Then this method, we can specify parameters, and that's what we are going to talk in the next video. But here I'm going to use the we have to use the mainframe .this .face detection .detect faces. Of course, I have to specify the file, so mainframe .this .file, and I have to specify the image panel. Mainframe, I like using this keyword, and image panel. You can skip it if you don't like it. Okay, so image panel. So that's all about. In the next video we are going to talk about the detect multi-scale parameters, and then we are going to test our application. Thanks for watching. Hi, in the last video we have seen how to implement the face detection with the help of the OpenCV classes and methods. And maybe you have a problem with loading the native library. So it can be solved very easily. You have to go to the properties, you have to go to the Java build path, and in the Java runtime environment system library we have a native library location, and we have to edit it, and you have to set it to something like this. I have installed my OpenCV to the C, so that's why you have to go to the OpenCV build path and you have to reference these files. I'm on a 64-bit system, whatever. You may be on 32. You can change it, but the easier part is to go here, OpenCV.build.java, and you just have to click to the x64, click OK, and that's all you have to do. And after that, you are able to run the application. So let's see, or face detection, and maybe we will have to tune the parameters. So I'm going to load an image. It is on the desktop, for example, Udemy, machine learning, face detection. I will have the second image. So I have an image like this, and I would like to run my face detection algorithm on it. I click on the detect faces, and let's see whether it's working fine or not. And in this picture, it is working quite fine, as you can see. It is able to detect all of the faces quite perfectly. Let's see another one. So load another image. I'm going to load the first image, this one, and I would like to run my face detection algorithm on it. And as you can see, it is approximately working fine. 1 face, 2 face, 3, 4, 5, but there are 6 faces, and there's a mismatch on the left. So maybe we should tune our algorithm. Let's see another one. The image 3. I think on this image it is going to, not going to work quite well. As you can see, there's lots of faces. As you can see, for the faces it is quite good. It managed to detect several faces, but there's lots of misclassifications on the lower part of the images, and there's one face that hasn't been classified, hasn't been detected. So that's why we have to tune the parameters, and that's what we are going to talk about in the next video. So thanks for watching. Hi, in this video we are going to talk about the parameters of the detect multi-scale method of the Cascade classifier. And why is it important? Because we have seen in the previous video that detecting multi-scale and detecting faces on an image is not so accurate with the help of the standard parameters. So we have to specify these non-standard parameters: the scale factor, the mean neighbors, the flags, the min size, and the max size. So we are going to talk about all of them. Of course, the image is the image on which we want to run our face detection algorithm, and the face detections are just this matrix we have specified. So this is face detections, a matrix of rectangles, and this is where we contain and store the references for the already detected faces. So I think these are pretty straightforward. The most important parameters are the scale factor, the minimum neighbors, and the minimum and maximum sizes. So what is the scale factors? Since some faces may be closer to the camera, they would appear bigger than other faces in the back. So the scale factor compensates for this. It's very important that it is going to specify how much the image size is reduced at each image scale. So the model has a fixed size defined during training in the .xml file. This hard, as you may recall, this is the model, this hard Cascade front face.xml. It is going to define the features according which we are going to detect whether it is a face or not. And it's very important that in this XML file we have a fixed size. So by rescaling the input image, you can resize a larger face to a smaller one and making it detectable by the algorithm. So the values of the scale factors should be between 1.1. It should be always greater than 1. It's very important. Should be greater than 1. And the optimal value is between 1.1 and 1.4. If it is small, for example 1.1, the algorithm will be slow since it is more thorough. It's going to process step by step, and it is going to calculate lots of things. So that's why it is going to be slow. If it is high, the detections will be faster, with the risk of missing some faces altogether. So there is some trade-off between setting it to small and high. It is going to be faster, but on the other hand, we may miss several faces. Okay, so what about the mean neighbors? By the way, you don't have to know about these parameters. You can have a guess. And this is for in machine learning, this is the so-called cross-validation. We try several parameters with several values, and we are going to get the one with the best parameters, I mean the best model. So the mean neighbors, it specifies how many neighbors each candidate rectangle should have to retain it. What are these rectangles? I have talked several times before rectangles. The rectangle are the one that's able to detect. We are going to use rectangles to show the detected faces. So the value interval is between 3 and 6. Higher the values, the less detections, but with higher quality. So if we set this mean neighbors parameters very high, there will be less detections, but with higher quality. As we have seen in the previous video, there's lots of mismatches. For example, sometimes elbows or toes are going to be detected as faces. So we can enhance the quality with the help of this mean neighbors method. The flags, it's not so important, it's kind of a heuristic. Reject some image regions that contains too few or too much edges and thus cannot contain the search object. It's very easy. That's why I talked about objects, because here we can specify our algorithm for detecting faces, but we can train our algorithm to detect, for example, cars or trees or houses. So that's why I talk about objects in the main, but here the object is a face. What about the mean size? It is objects smaller than that are ignored. So we can specify what is the smallest objects we want to recognize. It is usually 30 by 30. It is a standard value. The maximum size is objects larger than that are ignored. So for example, we have an image with a single huge face. Then we definitely have to set the max size to a concrete value, or we are not going to find our face because it's too large. We are going to see examples for that. So that's all about the parameters. Thanks for watching. Hi. In the previous video, we have been talking about the parameters of the Cascade classifier that detect multi-scale. And let's see why is it important. For example, I'm going to run my application, and I'm going to load an image of myself. It's going to be distorted, but it's important in the sense that the face we want to recognize is quite big. And if I run my original standard parameterized face detection algorithm, as you can see, there's a misclassification over here. It detected a face, but there is not. There is just a single face. And that's why we have to tune our parameters. So for example, I am going to set the scale parameter to 1.2, and then 3 flags is, for example, or the mean neighbors is 10. Then the minimum size is equal to 20 by 20, and the maximum size is equal to, for example, 500 to 500. What does it mean? That we are looking for images that has the minimum size 20 by 20, but I can set it up to, for example, 50.50, and we specify that the maximum size is 500 times 500. So we want to detect huge faces as well, and let's see how it works in practice. I'm going to load the image, and that's why these parameters are very dependent upon what kind of images we want to process, so detect faces. And as you can see, there is no misclassification now. We have managed to detect a quite big face. Okay, this image is distorted. I'm not going to bother about it, but the important fact that we have managed to eliminate false classifications. And if, for example, I'm going to load images, I think Udemy machine learning face detection, for example, image 2, these faces are smaller, but I think that this algorithm is going to work fine for this image too. Yeah, as you can see, we have managed to detect all of them. And I'm going to load, for example, the image 3. There was lots of misclassification. Let's see how its parameterized algorithm is going to solve this problem. And as you can see, it's much better. We have managed to recognize all of the faces except for this one. But there were lots of misclassifications, toes, hands, and so on, and we managed to eliminate it with the help of this parameter tuning. So we can butter around tuning these parameters. The scale factor is the most important one, and the sizes, as far as I am concerned. So this is how you tune these parameters, and these are the parameters description. Thanks for watching. Hi, in this section we are going to talk about and we are going to implement together an application that uses the same phase detection as we have seen for static images, but now we are going to use it for webcam applications. So for example, if I run this application, we have a user interface, and with the help of the webcam, we are able to detect faces real time. Okay, it's quite blurry, it is not so fast, my laptop is quite old to be honest, but anyways, it is working fine. So that's what we are going to proceed in the next videos. Thanks for watching. Hi, in this video we are going to talk about the user interface part of the webcam application. We have discussed in the previous section for the image application that this try-catch block, we need it in order to set the system look and feel. If we are on Windows, it is going to get the Windows look and feel. If we are on Mac, we are going to get the user elements. That's the basic feature and hallmark of Macintosh, and so on. So that's all about the user interface. Then we are going to instantiate a mainframe, and we are going to call the dataspace screen method. The main screen is going to store a reference to the detector. This detector is going to store the code for the OpenCV face detection. This camera panel is just to display the images getting from the webcam. Okay, so we have the title. We have to load the library, native library name, in order to be able to use the native library. So we have the instantiated detector and the camera panel. We set the content pane to the camera panel. So it is going to be the center in our screen, the camera panel. And with this, we just make sure that if we click on the exit, it is going to be quitted. We set the size and we set visible. Display the screen is going to, we create a matrix. This matrix is an OpenCV object because all of the images are transformed to a matrix. A matrix consists of numerical data, and we can make our algorithms on these matrix. The video capture is just to be able to manipulate the webcam, and while the video, if the video capture is open, so we try to open it, and while through it is just infinite loop, we read from the video capture. We specify that the webcam image is the one that we want to store the images itself. If the webcam is not empty, we do something. If it is empty, we just break out of the loop because there's some problem. We just set the size for the webcam. We detect the faces with the help of the processor. I mean, it is not the, sorry, I'm going to rename it. It is going to be the detector. Okay, so with the help of the detector, we are able to detect the faces. It is going to be approximately the same as we have seen for static images. Then we are going to convert this matrix to image with the help of the camera panel, and we are going to update the camera panel and going to repaint it. So the camera panel is basically, it stores an image, and we have this convert math to image. It is basically the same. It is exactly the same as we have discussed in the last chapter for static image recognition. And we have the paint component. We have these graphics. We have to call the super.paint component with the G graphics. If the image is null, we return it, and else we draw the image. Get the image height, get the image width, we get the image we try to draw, and so on. So we just draw the image on the screen, and in the mainframe we set the content pane to be the camera panel. So the whole user interface will consist only the camera panel itself. Next video we are going to take a look at the detector class. Thanks for watching. Hi. In this video we are going to take a look at the implementation of the detector class. In this class we use the Cascade classifier, and with the help of the Cascade classifier we are able to detect faces real time. So I'm going to store references to the detected faces. It is a matrix, consists of rectangles. We store a reference to the colored image, and we store a reference to the grayscale image. And in the constructor we are going to instantiate it accordingly. The Cascade classifier, we have to specify the hair cascade frontal face.xml file directly. I uploaded it with the source code. You can download and you can reference it. For me it is in the user desktop, and this is the XML we want to use. We have two methods, the detect and the show faces on screen. The show faces on screen is a method we have been familiar with in the static application in the last section. We just iterate through the detected faces, we get the array, and we just, with the help of this img proc, that rectangle, we plot the rectangles and we draw it on the screen. This is the starting point. The end point is the starting point plus the width and the height of the rectangle. The rectangle is the rectangle with which we denote the detected faces, of course. We have to specify the color. It is GBR, so not red, green, blue, but blue, green, red. And we have to specify the width of the line. Okay. This detect method get an input. This is the input frame. As we have discussed, OpenCV is going to transform the images into matrices, because this matrix consists of numerical data, and in programming we represent images with a matrix of doubles and so on. So first of all we are going to copy to the colored image and the grayscale image. With the help of the CVT color function, converts an input image from one color space to another. We try to, this is the image we want to transform to the grayscale image, and the color BGR, blue, green, red, to gray. So this is how we get the grayscale image. Then we equalize the histogram of the grayscale image. It's kind of a statistical stuff, consisting the relative frequencies of bits and so on. We have to use it, and we use this equalize hist on the grayscale image. So this is the target, and the source is the same. Then we use the Cascade classifier, detect multiple scale. With the help of this we are able, as we have seen earlier, detect the faces. And on the gray image, it's very important, and not on the colored image, but we try to use all algorithm in the gray image because it has a tendency to work better. And we are going to store the detected faces because we are able to detect multiple faces at the same time in this detected faces variable. It is a method_rect class. And as you can see, I use the standard parameters because for real-time phase detections, there's no need for parameter tuning in the main, and it's quite working fine, as I have discovered. Then I show the faces. With this method, I just iterate through the detected faces and plot the rectangles accordingly, and just return the colored image. So this is how we use it. I think it is pretty the same as we have seen for phase detection on images. And if I run this application, it is going to work fine. So if I run it, we're going to get the image we have been looking for. And yeah, it's working fine. It is able to detect the image. Whenever I go, it's going to detect the face. So that's all about face detection on real-time webcam application. Thanks for watching.